Fermat's little theorem is a theorem about remainders, and one way of saying is that a to the p minus a, is divisible by p if p is prime, and a is less than p. That's what it says. For instance, 2 to the 7th minus 2. 2 to the 7th is 128 minus 2, which is 126. And if you divide 126 by 7, you do get 18, remainder 0. It means it's divisible by 7 as predicted. So it's true theorem, and it means, for instance, that 11 to the 13th power minus 11, if I divide that by 13, I'll get remainder 0. So that's what the theorem is, that's what it says. Modern terminology, we could say this. It means the same thing. If you divide this by p, you get no remainder. We could add the a to both sides. That's also another way of saying it. And if we divide both sides by a, these are all things that are true. So I could say 2 to the 7th minus 2 is divisible by 7. I could say 2 to the 7th, if I divide that by 7, I'll get remainder 2. Or I could say that 2 to the 6th, if I divide that by 7, I get remainder 1. So those are all ways we use the theorem. Proving the theorem is a bit tricky. Take a look at Pascal's triangle for a second. One thing I want you to notice, 1, 6, 15, 20, 15, whoops, 6, 1, let's go at 7 rows, 1, 7, 21, 35, 35, 21, 7, 1. All the rows that have a prime number as their second number have in common that all the numbers inside that row, besides except for the ones, are divisible by the row number. So 3 and 3 is divisible by 3, 5, 10, 10, 5 is divisible by 5, 7, 21, 35, 35, 21, 7 is divisible by 7. Whereas these other rows, that's not true for it, like 20 is not divisible by 6, for instance. The reason that happens is because if you take like 7, all these numbers are combinations, 7C3, it's 7 times 6 times 5 over 1 times 2 times 3. As you can see, the 7 is prime. It's not going to get canceled out by anything in the denominator here, so it's going to be divisible by 7. Well, Euler's going to use this fact in his proof. So we're trying to prove that a to the p minus a is divisible by p. And he's going to start by saying, proving it's true for a equals 2. So he's going to show that 2 to the p minus 2, which can be rewritten as 1 plus 1 to the p minus 2. 1 plus 1 to the p can be expanded with binomial expansion. 1 to the p, this is pc1, which is just p, times, this is just going to be 1. 1 to the p minus 1 times 1, still 1. Plus pc2 is p times p minus 1 over 2 factorial times, these are just going to be 1s. So this is going to go on until we get to the last term, which is 1 minus 2. This minus 2 can cancel out with this plus 1 and this, and all that's left is stuff. All these other terms, these coefficients are all from the p row of Pascal's triangle, so they're all individually divisible by p, so the whole sum is divisible by p. And that proves that 2 to the p minus 2 is divisible by p, whatever p is. So then he moves on to say, well, what about 3? What about 3 to the p minus 3? Well, 3 to the p, 3 can be written as 2 plus 1 to the p minus 3. And when you do binomial expansion on this, you get 2 to the p plus p times 2 to the p minus 1 times 1 plus p times p minus 1 over 2 factorial times 2 to the p minus 2 times 1 squared. And the last term is going to be plus 1 minus 3. Now, these guys are all divisible by p. And this 1 minus 3 can be written as minus 2, so 2 to the p minus 2 plus all these p things here. But we already proved that 2 to the p minus 2 was divisible by p, so if this is divisible by p, and these are all divisible by p, then the sum is also divisible by p. And just to show one more thing, if I make a equal to 4, 4 to the p minus 4 could be written as 3 plus 1 to the p minus 4, which is going to be 3 to the p, plus a whole bunch of things with p's in them, plus 1 at the end, minus 4, so it becomes 3 to the p minus 3 plus dot dot dot. Each of these guys had p in them because of the coefficient in binomial expansions coming from that Pascal's triangle. We've already shown that 3 to the p minus 3 is divisible by p, therefore this whole thing is divisible by p, and that's Euler's proof of Fermat's little theorem.